Can you see my mouse pointer as well on the
Yeah,
slide?
it's
Good.
pink, right?
Excellent.
Nice.
Okay. So already live streaming. Yeah. So welcome everyone to today's seminar. Today we have Sebastian Kamann from the Liverpool John Moores University in the UK. He's going to be talking to us about young massive clusters and lots of things that you can do with them through integral field spectroscopy. So Sebastian got his PhD at the IAP in Germany, and then he moved to Göttingen for a first postdoc. And in 2017, he moved to the UK, to Liverpool, and since 2020, he is a UKRI Future Leaders Fellow. So thank you so much, Sebastian, for accepting our invitation. You may start when you're ready.
Right. Thank you, Anna, for the nice introduction, and thanks you all for listening in today. So before moving to star clusters, just one thing I wanted to mention is that when I agreed to this the seminar, I didn't notice that today was also the date of the solar eclipse in Europe. In the UK, it's only partially, and it starts after the seminar, so that's kind of good timing. But kind of we're a bit short on protective glasses, so that's why you find all these instructions online on how to build basically protective glasses from old cereal boxes. So yeah, that's kind of the astronomy-related headlines in the UK today. But anyway, we want to talk about star clusters, and I thought I should start this talk by a brief summary of what we understand under star clusters. So as we probably all agree, star clusters are gravitationally bound groups of stars that form from the collapses of giant molecular clouds. So that basically means that all clusters more or less have, or all stars in a cluster more or less have the same age and also share the same chemistry with some subtle differences maybe, but overall they're pretty much the same in that case. They're also almost free of gas and dark matter, and their evolution is dominated by the interactions of the stars with each other on the one hand. So they're collisional systems where stars constantly are in gravitational interactions with each other. And they're also their evolution is also governed by the tidal forces exerted by their host galaxies. And when we look at star clusters in the Milky Way, then we usually have this bimodality between open star clusters, so low mass clusters that are metal rich and typically less than a gigayear old, like the Pleiades that you see here on the slide. And on the other side of the scale, we have globular clusters, which have high masses, are mostly metal poor, and formed in the young Milky Way, so typically more than 10 billion years ago. And this is kind of the very basic view of kind of the families of star clusters. But I want to convince you today that actually our picture of star clusters, or the simplified picture, is pretty much biased, because already if we look at our nearest neighbors, the Magellanic Clouds, then we find star clusters like NGC 419 in the small Magellanic Cloud, which looks pretty much like a globular cluster, but is only 1.5 billion years old. In the LMC, for example, we have candidates like NGC 1866, which again is very massive, of the order of 10 to the 5 solar masses, but only 200 million years old. If we look a bit further afar, then we find even more massive young clusters, the so-called superstar clusters. For example, here's a cluster studied in a paper by Sebastian about 20 years ago, NGC 7252 W30, which was found to have a dynamical mass in excess of 10 to the 7 solar masses, so more massive than the most massive globular clusters we know of in the Milky Way, but has an age of only 500 million years old. And these superstar clusters are often found in galaxies that have ongoing or recent mergers experienced. So let's talk a bit about what actually governs the formation of massive star clusters. And here the property, the galactic property that's really crucial is the star formation rate density, because it defines the fraction of stars that are formed in bound clusters. So what was found experimentally or by observations was that the fraction tau of stars that form in bound clusters goes up if the star formation rate density goes up. Also, the maximum cluster mass that you form from star formation also goes up when the star formation rate density goes up. So basically, taking those two together means that in order to form massive star clusters, we need high star formation rate densities. And these conditions were mainly fulfilled in the early universe, but are not so much fulfilled in massive galaxies today. So in the Milky Way, the star formation rate densities that we have typically correspond to a fraction of bound clusters that is below 10%, so less than 10% of the stars form in bound clusters. And the maximum cluster mass is of the order of 10 to the 4 solar masses. But as I already mentioned, if we go back in cosmic history, and especially go to redshifts of about 2 or 3, the star formation rates densities on average were much higher. And that then explains why most of the massive star clusters that we see today are actually those old globular cluster type ones. But there are some exceptions. I already talked about mergers, and another exception is gas-rich dwarf galaxies. And in order to explain this, let's go back to the Magellanic Clouds. So what's shown here in this plot by Massana et al. Are the star formation histories of the 2 Magellanic Clouds. And what you see is for the large Magellanic Cloud, we had an initial burst of star formation and then a phase of relative quiescence. And then when the clouds started to interact with each other and with the Milky Way, the star formation rate went up again. Whereas for the SMC, there was more or less always some level of star formation going on. And when the interaction started, so these vertical lines here are close passages between the clouds, you see that they always led to kind of star formation events because the tidal forces resulted in gas turbulence and compression that then led to enhanced star formation, as we see in the plot. And that actually is reflected in the star cluster populations that we see across those 3 galaxies. So as I mentioned, the Milky Way had a very early assembly followed by a quiescent evolution. And that means that we have a very steep age metallicity relation here, and that most of the star clusters that were formed, the massive ones, are actually very old. What you can also already see in this plot is that there are some young massive clusters that are all associated with the Sagittarius dwarf galaxy. So another dwarf galaxy that formed its star clusters for longer. Moving to the LMC, we see that quite a few clusters formed in this initial burst, and then we have a period of quiescence, and then this recent kind of rejuvenation of the star formation then also led to the formation of new massive clusters. And for the SMC, again, we have basically also mirroring the star formation history, we have kind of an ongoing or a consistent formation of massive clusters throughout its history. One particularly impressive example of a young massive cluster in the Large Magellanic Cloud is R136, which we may consider as a globular cluster in the making. So this is the central star cluster of the Tarantula Nebula, the most massive star formation region in the local group. It has a mass of about 10 to the 5 solar masses. And also, interestingly, it hosts the most massive stars known. So R136A1, for example, has a dynamically confirmed mass of about 300 solar masses. And then that leads to the question, are clusters like this one actually gravitational wave factories? Because you have a lot of massive stars in a small volume, and then if these massive stars evolve and form black holes, then you would have a lot of black holes in a very small volume, and then the cluster dynamics would also favor the formation of binary black holes. And we actually see evidence for this process, that basically we form binary black holes and have gravitational wave events coming from star clusters. Because some of these binary black holes that have been detected by LIGO Virgo actually seem too heavy. So one famous example is this event GW 190521, which was the merger of two black holes with 85 solar masses and 66 solar masses to form a black hole with 142 solar masses. And the progenitors of this black hole form into the so-called pair instability gap, where actually the stars are so heavy that they are actually expected to disrupt completely rather than forming a massive black hole. And one solution to this problem could then be that what we have here is a hierarchical merger, where already the merging black holes are the result of a previous merger of lighter black holes. And this kind of process is only really feasible in star clusters, where you have a sufficient number of black holes that are in dynamical exchanges with each other to make this process feasible. But there's a big question mark here, because it's still unclear whether star clusters are able to retain their black holes, even if they form a lot of them. Why is this the case? Why are star clusters such insecure black hole hosts? For two reasons. First, because of their shallow gravitational potentials, and second, because of their short relaxation times. The first is a problem because black holes can be ejected via several mechanisms. For example, black holes typically during supernova explosions, when they form, they receive what's called a natal kick. And we can estimate the strength of these natal kicks by looking at X-ray binaries and looking at their height over the galactic plane. If we assume that all star formation happens in the galactic plane, and then also all the supernova happen in the galactic plane, then by looking at the vertical height of these X-ray binaries, we can estimate the strength of the kicks they received. And this is something that has, for example, been done in a study by Atri et al. In 2018. And here you can see the estimated kick velocities that the black holes in these X-ray binaries received. And they're typically of the order of 100 kilometers per second, or even more. The velocity that you need to escape from a star cluster is typically of the order of 50 kilometers per second. So it's likely that a lot of these black holes escape very early on. Also, when black holes merge, they receive recoil kicks, which again can be of the order of hundreds of kilometers per second. And then there's a third problem, which is the so-called Spitzer instability. Basically, if you assume a typical cluster where you have your massive stars forming black holes, after a while, there'll be the most massive objects surviving in the cluster, which means they mass aggregate to the center. And then Lyman Spitzer predicted basically that such objects should form a self-gravitating system, so kind of a subcluster inside the star cluster with a short relaxation time. And that would lead to all the black holes kicking out each other until there's only one massive black hole binary left. Now, more recent simulations have shown that the Spitzer instability isn't actually as efficient as initially thought, and that contrary to some previous studies, actually globular clusters can, for example, maintain sizable black hole populations over a Hubble time. And this then, of course, is also true for young massive star clusters. So it seems likely to, or it seems like a good idea to study or to search for black holes in star clusters, in especially young massive star clusters. And if we want to do this, then we also have to understand binary evolution. Because massive stars, those that form your black holes, typically live in binaries. And most of these binaries will interact at some point. And many of these evolutionary phases that involve interaction are actually very poorly understood. So here you have a typical kind of formation scenario that could lead to a binary black hole merger, where you start with two massive stars. At some point, one evolves off the main sequence, expands, and we have mass transfer, resulting in a stripped star. The stripped star might then form a black hole with a luminous companion. At some point, this luminous companion will expand, maybe forming a common envelope system with the black hole that leads to the ejection of the envelope. And then we have a black hole with another stripped star that then forms a second black hole. And only then we would have our binary black hole. And all of these phases that are described here are actually very poorly understood. So if we look at these young massive star clusters and try and then actually they give us a controlled environment in order to study these phases, because the ages, the metallicities, and the initial masses of the stars that are involved in these interactions are all pretty well known. So we can actually really use these objects to enhance our understanding of binary evolution and the pathways leading to black holes. Interestingly, though, if we look at the stars in star clusters, then they hold another surprise for us. Because what was found when the initial photometry observations of young massive star clusters in the Magellanic Clouds were performed was that their color magnitudes diagrams looked more complicated than one had expected, because these massive star clusters showed extended main sequence turnoffs. So here you have an example of a star cluster NGC 1846, which is about 1.5 billion years old. And you see that its extended main sequence turnoff is kind of, well, its main sequence turnoff looks kind of extended or even bimodal here, with kind of two branches that you might be able to see. Moving to even younger clusters like NGC 1866, which is 200 million years old, it was also found that not only the extended main sequence turnoff exists in these clusters as well, but also that it shows a split main sequence. So besides kind of the main sequence here, you also have a blue main sequence. And that raises the question, what are we seeing here? Why don't all the stars follow the same isochrone as you would expect if all the stars formed at the same age from the same molecular cloud? The initial idea was that we're seeing evidence for age spreads here, where basically in this case we would have had two star formation events that resulted in the formation of this cluster. But there's a problem with this explanation, because it was found that the inferred age spreads increase with the cluster age. And that seems rather unlikely that the formation or the duration over which a cluster forms its stars depends on its age. And instead it points to a stellar evolutionary phenomenon, namely stellar rotation. Why would stellar rotation give you photometric spreads? Well, stellar rotation changes how a star looks like in several ways. First of all, it breaks the spherical symmetry. So the observed properties of the stars then depend on the inclination. And this is referred to typically as gravity darkening. So here you see two examples of how this gravity darkening can be modeled, where basically you have a rotating star and the equatorial regions, which are farther away from the core, then appear cooler than the polar regions, which are closer to the core. So you basically have a temperature gradient across the surface of the star. How this temperature gradient looks like is still being debated, as you can see from the two possible calculations that are shown here in this example. Stellar rotation also changes the hydrostatic equilibrium of a star. As we all know, the stars are kept in balance by basically gravity pointing inwards and pressure pointing outwards. Now, if we rotate the star, then we have a centrifugal force supporting the pressure. So kind of the effective temperature of the star drops, changing its colors. And also we can have additional mixing induced by the rotation, which then again impacts how a star looks like in a color magnitude diagram. And as was shown in a study by Sebastian and Mink in 2009, if you take all of these effects together, then they can actually explain the observed photometric spreads, as shown here in this simulated color magnitude diagram of a star cluster with a simulated age of 1.5 billion years. But can we actually measure how fast the stars in these clusters rotate? And coming back to the black holes, can we actually also study the binaries in these star clusters and look how these poorly understood, say, interaction phases look like? And in order to do this, we need spectroscopy, because spectroscopy is the key to study stellar rotations and binaries alike. First, because we can estimate the projected rotation velocity of a star by looking at the line broadening. So if we start rotating our star, then our stars will get broadened. Our spectral lines will get broadened the faster the star rotates. And then we can use the same spectroscopic lines in order to study radial velocity or line of sight velocity variations that would reveal the presence of binary stars, and then allow us to study these systems in more detail. The problem is that these clusters are not really well suited for spectroscopy, because they're very dense stellar fields, and they're also very distant. So basically, the only way we can really do this is if we have 8-meter class telescopes and use integral field spectroscopy. And the instrument that we've been using in order to study these phenomena over the previous years is the MUSE integral field spectrograph at the ESO Very Large Telescope. And this is basically a summary of the MUSE observations that we took of young massive star clusters in the Magellanic Clouds over the past years. So we basically cover, say, of the order of a bit less than, not all the clusters are shown here. I think our total sample is of the order of 10 clusters, covering basically something from 100 million years to 1.8 billion years. And this is more or less the age range where really stellar rotation, for example, is supposed to have a measurable effect. I'll focus now first on this candidate here, NGC 418, before moving on to the sequence of 3 young massive clusters between 100 and 300 million years for the remainder of the talk. But let's first look at NGC 419, which is 1.5 billion years old. And the power of MUSE in studying these objects is that here you have the MUSE field of view. And then really for all the stars that you can see in this image, we get a complete spectrum. And I've highlighted 2 stars here with these circles. And you can see a small spectral range from the full MUSE spectral range here. And what you can already see is for the star highlighted in red, the calcium triplet lines are much broader than for the blue star. And this basically allows us then for both stars using full spectrum fitting to estimate the projected rotation velocities of those 2 stars. And what we find here is that indeed the blue star is a slow rotator with a projected rotation velocity of only about 45 kilometers per second, whereas the red star is rotating much faster, of the order of 160 kilometers per second. Now, if we do this for all of the stars in our sample, then we find a clear link between the photometric color of a star and its projected spin velocity. So here you see the color magnitude diagram of the cluster, color-coded by the spin velocities that we measured. And you can clearly see that across the extended main sequence turnoff, the redder stars rotate faster. Now, if we look a bit into more details here, then we see that there's actually a bimodal V sin I distribution here. So we have one peak of slowly rotating stars with less than 100 kilometers per second, and one peak of fast rotating stars of the order of 150 kilometers per second. And what we can now also do is to go down in magnitude, which means we also go down in stellar mass. And what we see then is that basically at a certain magnitude and a certain stellar mass, the fast rotators start to disappear. And this can be explained by what's called the Kraft break. So if we go below a stellar mass of the order of 1.4 solar masses, which we reach here at a magnitude of about 21.5, then the stars below this mass will have convective envelopes. And convective envelopes then usually means that the stars also have magnetic fields and stellar winds. And the combination of magnetic fields and stellar winds is very effective in magnetically breaking the stars. So what we see here is basically that even if we had initially, when the cluster was born, fast rotating stars, they would have been braked by magnetic braking. And this nicely coincides with the disappearance of the photometric spreads, which then adds additional evidence that what we're seeing here is really the impact of stellar rotation on the color magnitude diagrams. Now, moving on to the younger massive clusters, we find a very similar picture. So here we have NGC 1850, and down here we have the split main sequence. And again, what we find is that on the blue main sequence, we have predominantly slow rotating stars, whereas on the red main sequence, we have predominantly fast rotating stars. And we observe the same picture for the other two young massive clusters, NGC 1866 and NGC 1856. And what we can now do is basically we have an age sequence from 100 to 200 to 300 million years. And then we can pick a narrow magnitude range in all of those clusters, which then would correspond to a narrow mass range. And then using these three clusters and a given stellar mass, we can study how rotation changes as the star evolves. And that's what we did for the fast rotating red main sequence stars. What we did is we did a statistical correction for the inclination, which allowed us to estimate the mean spin velocities of the red main sequence stars for these clusters. Here's only two of the three clusters shown, NGC 1866 and 56. And here we see that basically in both cases, we find mean equatorial velocities for the fast rotators of the order of 300 kilometers per second. We can also repeat the same exercise for the blue main sequence stars, in which case we get spin velocities below 100 kilometers per second. But let's stick to the fast rotators now. What we can then show is basically here we have the cluster age, and here we have our measured mean spin velocities. And what's overplotted in blue here is a prediction on how the spin velocity should evolve for for a star with about 3 solar masses as the star evolves on the main sequence. And basically what you find is that apart from an initial drop when the star settles onto the main sequence, these stellar evolutionary models, which were done by the Geneva group, basically predict that the spin velocity doesn't really change. And this is also what we observe. But what's also shown here is the critical velocity. That's the dashed line here. So the critical velocity is the maximum amount by which you can spin a star before it starts basically disintegrating because of the centrifugal forces. And because as the star evolves, basically the core contracts and its hull expands, the critical velocity is supposed to drop. And that's what you can see here by this dashed line. Now taking those two things together, we can basically calculate the ratio between the actual spin and the critical spin. And what we find is that basically as we approach the main sequence turnoff, those two are pretty close to each other. So these stars, when they reach the end of their main sequence lives, should be rotating very close to their critical velocity. These almost critical rotators also are a well-known phenomenon because stars spinning near their breakup velocities form what's called decretion disks. So they basically, in their equatorial plane, they shed material and then this material is ionized by the radiation of the star, leading to line emission. And these stars are then known as AE, BE, or OE stars. And the E here stands for emission. So these are early type stars with emission lines in their spectra that are a result of fast rotation. And if we look at our MUSE data quite carefully, then we find hundreds of these BE stars in the MUSE data. So what's shown here on the right is basically two false color images created from the MUSE data of NGC 1866. And this down here is NGC 1856. Sorry for the typo. And all the stars shown in red here. So red is H alpha, and green and blue are two other emission lines. But all the red points here are H alpha emitters. And you see there's a lot of these H alpha emitters, which are all basically BE stars. And we actually find most of them near the turnoffs of the two clusters. So here are the positions of the BE stars highlighted in the color magnitude diagrams. And you see two things here. You see that they're really confined to the redder part of the CMD, whereas we don't have any objects here. And this makes sense because these should be the slow rotators in the clusters. And what you also see is that in the older clusters, the population of BE stars extends further down in magnitude, so extends to lower mass stars. And this makes sense relating to the picture that I just showed you, that basically only when stars reach the end of their main sequence lifetimes, they turn on this BE phenomenon. Now we can do some statistics of the number of BE stars. And this is shown here. Basically, this is the fraction of BE stars as a function of the absolute magnitude of the stars. Here we have the older clusters in the sample. Here we have two younger clusters. And what we see is that, again, we see that both in the older clusters, BE stars appear at fainter absolute magnitude, so at lower stellar masses. And also we see that the fraction of BE stars in all of these clusters reaches of the order of 50 to 60% near the main sequence turnoff. And this suggests that actually most of the stars evolving in these clusters are likely to become BE stars just before leaving the main sequence. And this is interesting because it basically suggests that you can form BE stars just from plain single star evolution. But what we observe in the field is that most BE stars are actually spun up by mass transfer in binary systems. So we have these two channels, the say single stellar evolution channel that seems to be dominant in these clusters that we studied, and the binary channel that seems to be dominant in the field. But the overall importance between these two channels is still debated. So that's also some room for future studies. And that brings us to the question, what causes these peculiar spin distributions that we observe in these young massive clusters? Why are most of the stars rotating very fast? And there's a subpopulation of stars of the order of 20 to 30% that are rotating slowly. One of the scenarios that was proposed to explain this would be that binary stars are in play. That basically you have tidal interactions in tight binary systems that slow this, that basically spin down the stars. This was based on an observation by Abd and Bonyarak in 2004, who studied stellar rotation in binary stars and found that if they went down in period, at a certain period below 500 days or so, the stars were spinning slowly compared to the non-binary stars. And this was explained via tidal interactions in these binary systems spinning down the stars. Another possibility that has been proposed is that basically binary mergers during the pre-main sequence stars lead to the slow rotators. The idea behind this is that these merger products would be rejuvenated, so would appear bluer than they should be, And this could explain why in a lot of clusters, the blue main sequence is actually bluer than what's predicted by isochrones. So here you see an example of an isochrone for slowly rotating stars, which doesn't quite seem to match the colors of the slowly rotating stars in the cluster. And in this paper by Wang et al., they proposed that binary mergers could be a way to reconcile models and observations here. One scenario that we proposed in a study led by Sebastian would be that it depends on the lifetimes of the protostellar disks. But basically, if the stars settle, when the stars settle onto the main sequence, then they can be efficiently braked if they have a disk, because the disk might couple to the star and then control its angular momentum. And this, what's plotted here, is basically how this spin velocity would change if you have a long-lived disk that would basically break the star. However, if your disk is evaporated, for example, by the presence of a nearby O star, then the star would spin up to a much higher velocity. So these are the three main scenarios that have been proposed. So far, there's no clear-cut answer on which of these mechanisms is the most important. So this also leaves room for further study. In the last 10 or so minutes of my talk, I want to discuss binary stars in more detail and want to come back to the question of, do we find black holes in young massive clusters? And what about young massive clusters as maybe being gravitational wave factories? Can we say anything about this? Now, binary studies in young massive star clusters are very challenging, because contrary to the stellar rotation science case, you actually need multiple epoch observations. So you need a lot of observational data, and then you need to measure the radial velocities quite accurately. And the problem when using MUSE is that the early type stars that we're interested in the MUSE spectral range only really have broad lines, which means we can't measure the velocities that accurately. So we only have results so far on the binary science case for the youngest cluster in our sample, NGC 1850, which we observed over 15 epochs. And then our aim here is to find binaries via line of sight or radial velocity variations. And if we do this, then we can make a color magnitude diagram like this one here, where basically the probability of the stars to be in binaries decides upon the color coding of the stars. So the black points are the likely binary stars. And then those highlighted in red are those where we're really certain that those are binary stars. And if we calculate the numbers here, then we find that this cluster has a binary fraction of about 20%. And this we can compare to other clusters that have been studied for their binary populations. And what you have here is basically, you have the binary fractions plotted on the y-axis. And we have here young massive clusters. And here you see the stellar masses that have been studied. And here we have the globular clusters. And what we find is that in the young massive clusters, the binary fractions are higher than what we observe in the globular clusters. And this is likely a combination of two effects. First, the cluster dynamics are predicted to disrupt a lot of binaries as the cluster evolves. And basically, they had more time to disrupt binaries in the older clusters. But also, we know from the field that massive stars are more likely to be in binaries. So here you have the binary fraction as a function of stellar mass in the field. And we see here that this strongly increases as we go to more massive stars. And it's also higher than in the clusters, which is likely then a result of the binary disruption via the cluster dynamics that we observe in all of the clusters. But let's focus on NGC 1850 now. So here we have again the color magnitude diagram. And what we can now do is we can try and, for the binaries that we found, try and infer their orbits. But this is really challenging because basically we only have a few data points, but there's an infinite number of orbits that you can fit to them. And this work has been pioneered by Sara Ciarcino, who was a postdoc in Liverpool before moving to Florence last year. And she used advanced statistical methods, tools called the Joker, in order to find which of these binary stars, for which of them can we actually measure the period. And if we're lucky, then all the possible solutions to a given radial velocity curve, basically all these possible solutions then either have the same period, or we have just basically two families of orbits in which we have unimodal or bimodal solutions. And those are really the systems that we can then pick out for further studies. And here these systems are shown, and what's shown here is their period on the y-axis and basically the radial velocity amplitude on the x-axis. And if we have these two quantities, we can estimate the companion masses. The more massive your companion will be for a given period, the higher your radial velocity amplitude will be. And if you translate this idea into this plot here, then you can basically draw a line, which is this dashed blue line here, where basically the companion that we don't see must be more massive than the star that we see. And these are then the prime candidates where we could have a remnant as a companion, because a remnant would be more massive than a primary, especially when it's a black hole, but wouldn't emit any light. So these are the stars that are very interesting. These are the potential black hole candidates or potential black hole companions in this sample. So let's have a closer look at one of them, which is this star down here. So here we have the interesting stars highlighted in the color magnitude diagram. Basically, those with potential black hole companions are those three stars up here, and then this guy down here, BH1. Here's the radial velocity curve for this system, NGC 1850 BH1. And it's also a photometric variable. So we also have light curves, which then allow us also to estimate the inclination angle of the system. And if we basically take this information together with the known position of the star in the color magnitude diagram. So in the color magnitude diagram, the star sits right on the main sequence turnoff. And if you assume single stellar evolution, then that corresponds to a mass of about 5 solar masses for the primary, or 4.5 solar masses. And assuming this, we find a companion with a mass of 11 solar masses, which can only be a black hole. But there's an alternative explanation here, because there's also the possibility that the star that we observe is a post-interaction binary that's actually much lighter than what we would assume or what single stellar evolution would give us. And if your primary star is much lighter, then you can also get away with a lighter companion, which in this case might be a fast rotating BE star. And then this system would be a so-called black hole imposter. How can we tell the difference between the two? There's a fancy method which is called spectral disentangling, which is basically you have an observed spectrum where you see some clear variation between your epochs. And what you then do is you model this spectrum as two spectra of two luminous companions that are moving in antiphase to each other. Doing this type of analysis on the MUSE data is very challenging because the MUSE data has a very low spectral resolution and also doesn't cover the spectral range that we need. So we took follow-up observations of this system, NGC 1850 Black Hole 1, using the FLAMES Argus integral field spectrograph. And here you see that FLAMES compared to MUSE isn't that great when it comes to spatial information. But here we have our system and we got useful spectra for it. And what the analysis of this data then revealed, so this is an analysis that was performed by Ries Seeburger, who's a postdoc now here in Liverpool. And he applied the spectral disentangling, and he could really reveal the presence of a second luminous companion in this system, which is actually contributing 50% of the light in the blue, because it's actually much hotter, 18,000 Kelvin, than the known star, which has only 11,000 Kelvin. And this difference in effective temperatures is also why we couldn't see it in the MUSE data. As expected, a revealed companion is rotating much faster than the primary that we initially observed. And what's also interesting is that the orbital period of basically our known star is 180 kilometers per second, and it's barely measurable for the secondary, which means that this companion must be much more massive than the star we initially observed. So what happened to this system? What we assume is we basically initially had a binary of two almost equally massive stars. Then one of them left the main sequence, started expanding, and we had Roche-Lobe overflow. And this Roche-Lobe overflow then spun up the companion star. At some point, mass transfer stopped, and this star had shed most of its mass to the companion. And after mass transfer stopped, it now lives in a short duration phase, which is called a bloated phase, where despite the star only having a mass of 1 solar mass or so, it's still as bright as a 4 solar mass star. And then basically this is where the predicted positions of the stars in the color magnitude diagram are. And if you combine them, you end up with something that looks like a main sequence turn-off star. Now the future evolution, basically our donor star will shrink and will become what's called a subdwarf B star or so. And then we'll only be left with the fast rotating E star and a barely visible companion in a few million years from now. So is this puzzle completely solved now? Not quite, because as I already mentioned, this companion that Reese revealed is barely moving, which suggests it must be much more massive, of the order of 10 times as massive as the primary star. So this donor star must have been strongly stripped, and the companion accreted substantial mass. And then what we can do is we can plot our system here in a diagram plotting period over the mass ratio. This is shown here. And then basically below a period of about 1 day, the stars would actually touch. And what's happening if mass is transferred from one star to the other is that basically widens the orbit. And what we can do is, assuming certain prescriptions for the mass transfer, we can then backtrack the evolution of the binary system. But if we do this, so basically here we have how the system must have looked like in the past. And if we do this, basically that we find that if we assume what's the kind of default assumptions for how mass transfer works, this system actually doesn't work, because at some point the stars should have touched. So this probably tells us that our idea of mass transfer still requires some refinement. So this is something that we're currently working on in order to really fully understand this peculiar and very intriguing system. Before concluding, what's the outlook? As you've already seen on the previous slides, there's more interesting binaries that could maybe potentially host a black hole companion. They also have very interesting spectra. So here's one candidate shown. I think it's this one, number 47, where in the MUSE spectra, we have basically all of the spectral lines in emission. And in the case of the Paschen lines here, it's actually double peaked emission. And if you look at H alpha, you can actually see the phase of the orbit in the line profiles. But then basically the line profiles differ between H alpha, H beta, and the Paschen lines. So there's all kinds of crazy things going on here, and we're still trying to make sense of these spectra. So yeah, this is something that's currently ongoing. Looking even further into the future, MUSE is probably not ideal for studying hot stars, because in these cases, most of the interesting and narrow spectral lines are below 5,000 angstrom, which is where MUSE cannot go. So I think in order to push these studies further, blue MUSE will be much more suited, which is supposed to come online in the next decade at the VLT. And one project I'm also involved with at the moment, which will take this even further, is what's called the Wide Field Spectroscopic Telescope, which is a proposed 12-meter telescope that would be purely for spectroscopy, combining a gigantic IFU of 3 by 3 arc minutes in the center with a MOS with 30,000 fibers over 2 arc minute, 2-degree field of view. And this all at a dedicated facility. And just to illustrate what one could do with such a facility, here's another view of the LMC. All the colored dots here are massive star clusters, color-coded by their ages. And with WST, one could then really do a comprehensive study of the entire LMC using the IFU to cover the star clusters and the MOS to cover the surrounding field. And then basically get a comprehensive picture of the entire LMC binary population. If everything works and if this WST is ever approved, then this will be feasible in about 20 years from now. So might still be interesting for the younger people in the room to do observations with this thing. Let's see. Anyway, this brings me to my take-home messages, which is basically 2 take-home messages. I think that the color magnitude diagrams of these young star clusters are shaped by 2 processes: stellar rotation on the one hand and binary interactions on the other. And this we could really show using MUSE observations. But what we still need to answer is what sets the stellar spins in these clusters, and how many black holes reside in the clusters, and how many of these black holes have luminous companions. And with that, I'd like to thank you for your attention. Apologies for running slightly over time, but I'm happy to take any questions.
Thanks, Sebastian. Thank you very much for a very nice talk. Do we have questions? Neil, can you hear him?
Can you hear me?
Yes, I can.
Okay, so very interesting talk. My question was when you mentioned that you use MUSE spectra to measure the velocities, and as we saw that it's a very crowded field. So how did you handle the source confusion while measuring the velocity?
Yes, that's a very good point, because I brushed over it. What we do, so this is actually, this takes me back to my PhD days, because one of the tasks I had during my PhD was develop a software to deblend stellar spectra from these MUSE observations of crowded stellar fields. So what we're doing is we're basically recovering the point spread function of the observations, and then together with a HST based prior on the positions of the stars, we use this to deblend the spectra of overlapping stars. Yes, this process, this algorithm then was implemented into a software package which is called MUSE. And that's freely available online to use and experiment with.
Wanna go?
Yeah, so I'm also dealing with some same problem, but I'm not. Yeah, I'm measuring velocities too. The thing is, even though we use MUSE and PSF information from HST, the velocity or the line mixing is still there. So did you verify for that, or was there something that was there some assumption that was made before doing this?
It's I mean, we didn't make any assumptions here. I mean, all that we assumed were that the HST positions are valid and that we can recover the PSF. So I think it then depends on, yeah, it's hard for me to say, right, why it shouldn't work in your case. I mean, it should. So yeah, this is probably something, if you show me the data, I'm happy to, to have a look and understand why it might not be working in your case.
Okay. More questions from the audience? Thaisi?
Hi, Sebastian. Thank you very much for your talk. About the companion, we know that gravity also broadens the lines. So could that hot fast rotator be a hot high gravity star?
Yes, so it's the gravity of the star is fair. I mean, it's main sequence like. So it's of the order of 4 or so. So it's, yeah, I think it would be hard to go even higher than that. So I think for the black hole companion, it's not so much an issue. In the case of the I think in the case when we study stellar rotation, of course, we also have to take the broadening from other effects like gravity into account. But they're usually only these effects are of the order of, say, up to 10 kilometers per second usually. So with the velocities that we're concerned here with, yeah, we kind of neglect them.
Do you have more questions?
Maybe I'll ask one. Hi, Sebastian. As usual, excellent talk. I want to ask something about actually one of your earlier slides about the multiple black holes being formed at the beginning and whether or not you might have them all kind of bundled together in the center or have them ejected. I was wondering if this is a testable scenario in the sense that if there are a bunch of black holes being ejected, then there would be a few, I guess, for lack of a better word, free-floating black holes around. Wouldn't, even if they're rare, they would have high or higher lensing signatures. So wouldn't microlensing surveys detect a bunch of these black holes lying around? I don't have a good idea of the numbers or anything like that, but I was just wondering if this is a testable scenario.
Yeah, that's a very good point, Joao. Thanks. It's observationally, I think it's really hard to test. So basically, we're mostly relying on the predictions of n-body models at the moment. I think going forward with gravitational wave detectors, I think one parameter that has a very high kind of discriminatory power is the relative spin orientations of the black holes in binary black hole mergers. Because basically from evolution, from single or from isolated binary evolution, you would expect the spins of the merging black holes to be aligned, whereas they could be in all kinds of random orientations if they're coming from a cluster. So if we would find a lot of merging black holes with misaligned spins and no clusters in that vicinity, then I think, yeah, that would really be a telltale sign for escape of black holes from star clusters.
Cool. Thanks.
Cool. I have a question regarding metallicity. So you're here in the Magellanic Clouds, you're looking at higher metallicities. Like when you go to the earlier universe, what do you expect would be the differences that you would be seeing in terms of your work with stellar rotation and binaries affecting the stellar population of galaxies?
Yeah.
Kind of a convoluted question. I hope I was clear. Sorry.
Yes. So in terms of stellar rotations, stellar rotation, it's a very good point. I actually didn't look at how metallicity would change the stellar rotation properties. I would imagine it to have at least some effect because, for example, the additional mixing that is actually responsible for a significant fraction of the photometric spreads that we see might be less efficient. So yeah, but I don't have a really good answer to this to the impact on the stellar rotation. I think from the black hole side, what we would expect would be that on average we should find more massive black holes than at high metallicity because stellar winds should be weaker. But yeah, I think that's an interesting question to study the metallicity dependence of stellar rotation.
Okay, thanks. We have one question from online before we let you go see the eclipse.
Don't worry, it's still a while. You don't need to cut this short.
The question is, I was wondering how you knew that you would see both the binary component signatures before taking spectra in flames, like about your justification for time.
Yes.
Yeah.
So basically, there were these two possibilities out there, right? That we would either have a black hole in there, in which case we shouldn't find a second component, or we have one of these black hole imposter systems, in which case we should see two stars. So in that case, even if we wouldn't have found the second star, by the spectral disentangling, we would have been able to put an upper limit onto the contribution of any companion. And then if that upper limit is below a certain fraction of the total light, then the star just can't be massive enough anymore to explain the observed line of sight velocity variations. And in that case, we could then confidently have said that this is a black hole.
Okay. Thank you. We have one last question from Sandra.
Hi, Sebastian. Can you hear me?
Hey, yes, I can hear you fine.
So it was just it's a curious question for NGC 1866 from the MUSE image that I saw. So you mentioned the green color was due to some emission lines, right? But you didn't mention the exact emission lines. And also in the right side, I saw one circle, green circle, which is quite different from the point source. What was that?
Oh, yes, that's a very, very good point. So in this case, the green color is a nitrogen line. It's nitrogen 2, I think 6717. And blue in this case would be the oxygen 3 line at 5007 angstroms. And this green circle here that you spotted, good catch, that's a planetary nebula that was previously unknown. And we just discovered it by chance in the MUSE data, because we found these weird spectral lines in the stars around this area. And it's an interesting object because the cluster is actually almost too young to show planetary nebulae, because we have turn of masses here of the order of 4 solar masses plus minus. And it's expected that for these stars, the post-AGB evolution is too fast so that the star can't actually ionize the planetary nebula. So there's a separate paper about this object that was led by Howard Bond last year, that discusses all of these objects in detail. Kind of very brief private note is that this is the only object in the sky with my name, because I discovered it, and then apparently in the planetary nebula community, whoever discovers the system is named after. So anyway, this is LMC-KA1.
Oh, interesting fact. More questions? If not, let's thank Sebastian again. And I'm very happy you guys asked lots of questions. Cool. Thank you. Enjoy the eclipse.
All right. Thank you. Thanks for having me.
Right.